Hey everyone, welcome to another video. Today we're talking about the second part of our obtuse angles and exact values portion of this course, and we are focusing on these exact values in this particular video. And we are applying this to two very significant triangles when it comes to trig ratios. We have this one on the left here. So a triangle, this is an isosceles triangle because these two sides are equal and they both have a length of 1 and a hypotenuse of root 2. You can check this via Pythagoras if you'd like. And as we discussed before, these are ratios. So this doesn't just apply for when we have 1, 1, 2. It's going to apply for other similar triangles as well. So we're going to see a lot more of this, particularly in the later years. And we have another right angle triangle here, the lengths of 1, 2, and root 3, and a couple of different angles here of 30 degrees and 60 degrees. Now, these three angles, 45, 30, and 60, these are quite significant in terms of trigonometry when we look at certain future applications of trig in later years. So in this video, we're not going to get into that too much. We're just going to introduce these ratios and figure out the exact ones using SOHCAHTOA, which we've been doing before. And we're going to fill out this table with a bunch of significant angles here, ranging from 0 to 90 degrees. So let's get straight into it. And this video is just going to be introducing this idea, filling out this table, and the next video we're going to be looking at explicitly. We're going to look at explicitly going through some practice questions of this sort. So if we looked, for example, first at this triangle on the left. So I want to find all of the ratios here. So I'm going to do sine of 45 first, and that's my opposite over my hypotenuse, because from SOHCAHTOA, let's actually write this here in case you've forgotten, so we have it for reference. SOHCAHTOA. So sine links my opposite and my hypotenuse together. So this gives me sine of 45 degrees equals 1 over root 2. And we can also rationalize the denominator here as well. And we can also write this in a different way, root 2 over 2. You can pause the video, have a go at rationalizing the denominator if you'd like. Now, cos of 45 degrees, this is the exact same thing because cos links adjacent and my hypotenuse together. Whoops. So I have this side and this side. So that's going to give me the exact same thing. And if you look back at the table I used in the previous videos, you should see as well in those ratios that sine 45 and cos 45 are exactly the same. And this makes sense because the lengths of the adjacent and the opposite are exactly the same. Beautiful. And we have our tan of 45. That's my opposite over adjacent. Gives me 1 over 1, which gives me 1. Okay. Let's come up with a couple more. Well, actually, let's just fill these in, shall we? So we have for sine 45, so we have root 2 over 2, root 2 over 2, and 1. Okay, let's look at 30 degrees now. So sine of 30 degrees, that's going to be my opposite over my hypotenuse, so 1 over 2. So this is one of those really nice examples we get. So if you look back at the trig ratio table that we looked at many videos ago, you can see that we got an 0.5, for example, once, which was a really nice number. We actually used that in an example too. So we have cos of 30. That gives me root 3 over 2, because cos is adjacent over hypotenuse. And finally, tan of 30 is opposite over adjacent. So we have 1 over root 3, which we can write as root 3 over 3 also. Okay, filling this in. Now this is just an exercise in starting to fill out this table. We're going to look at this in way more detail, and in this video we're particularly going to look as well at explaining these two here based on what we currently know about trig. Okay, at the very end we're going to try the 60 degrees here. So first of all, my sine of 60 is going to be root 3 over 2, because I have my opposite side to the angle, and my hypotenuse gives me root 3 over 2. My cos of 60 gives me 1 over 2. So we can already see some similarities kind of happening. So you can see that this one links to this one. This one here is the same as this one. Actually, let's color code those a little differently. This is the same as this. So hopefully this is sparking a little bit of interest and thinking, well, why are those the same? Now we're going to look at this way later when we look at some more trig identities, but we're already piecing some things together here, some really interesting patterns that come up. Okay, finally the tan of 60, that is my, let's do this in a different color. That is my opposite over my adjacent. So root 3 over 1, which just gives me root 3. Okay, let's plot these in, and we can finally move on to talking about these other bits. 1 over 2, and we have root 3. Okay, so let's look at when we have these really extreme angles, 0 and 90. Now this is really hard to kind of visualize with just right angle triangles, which we've done before. But I'm going to run you through a couple of thought experiments so we can fill out this table. And later on, particularly next year, in next year's content, we're going to look at the unit circle and look at how we can show these as well using the unit circle. Now imagine we had an angle of 0. So say this is my theta. And let's see what happens as my angle approaches to 0. So I currently have an angle here. Now, as this gets smaller, as my angle gets smaller, you will notice my opposite gets smaller. So it goes from here, down to here, down to here. And as this approaches to 0, you're going to see that my opposite is going to get so tiny and minuscule, it's basically going to give me, when I round it to the nearest whole number, that's just going to give me 0. Think back to when we did the very first video on this topic. That's why I gave you a really long introduction. We're talking about ratios here. So here we're going to have a really small number. If you remember back from those trig tables in the examples we did, the values for like 1 degree or 2 degrees were these like 0.00 really small numbers. So if we take that, we divide it by the hypotenuse, we're going to pretty much get, as we approach an angle of 0, we're going to get a sine ratio of 0. Now, let's look at what happens with the cos if this was 0. So we have let's just look at a triangle. So here, if we have a regular triangle with some theta, as this gets smaller, then we're going to have as we get really tiny, we looked at this before, we're going to have an adjacent that's so close to the hypotenuse that as this angle approaches 0, the lengths of the two are going to get so close together that their ratio is going to approach 1. Because a number over another number that are really close in value, so let's say this was like, I don't know, 0.99, and this was 1, they're going to roughly give us, when we round it off, a ratio of 1. Now, this was very characteristic in our tables that we looked at before, where we looked at these really small angle values. So, for example, the angle value of 1 degree was like 0.9998, something really, really close to 1. So that when we round it, we effectively end up at 1. And finally, we're looking at tan. Now, tan is the ratio of opposite to adjacent. So as we get a really small right angle triangle, I'm going to have something that's approaching to 0 divided by something that's approaching to 1. So my tan ratio is going to be 0 divided by something. That's going to give me 0. 0 divided by any number gives me a 0. Okay, let's look at another extreme case when we have 90 degrees. Now, this is obviously going to be quite... Some of you may be thinking this is kind of impossible because we already have a 90 degree angle here. So this becoming 90 is just going to stop being a triangle. But we want to just imagine this idea of getting really, really close to 90. So if this angle was something like that, a really big angle that's close to 90. In this case, what's going to happen between the opposite and hypotenuse is going to be something similar to what was happening with the adjacent and the hypotenuse for cos in the previous example. They're going to get, because my adjacent's tiny here, but my opposite is very close to the length of the hypotenuse. So close that the ratio of one to the other, they're so close that it's going to pretty much approach, it's going to approach 1. So that is going to be my my ratio here. Okay, so for the next one, we're looking at cos, and we're going to see a similar thing happening, just the reverse thing happening, but for what happened with sine for a small angle. Here, cos is going to get, sorry, not cos, the adjacent's going to get so tiny as the angle approaches 90 degrees that its ratio to the hypotenuse is going to be really, really small. So it's going to get so small that it's going to approach 0. Now let's look at one more thing, and this is the weird one. We're going to look at what happens for tan of 90 degrees. Now, tan is the ratio between the opposite and the adjacent. Let's underline that one too. Now, let's zoom in a lot on this triangle. It probably doesn't even look like a right angle triangle anymore, to be honest, because the other angle is so big. But if we look at how these are changing, as the angle gets really big and approaches 90 degrees, I'm talking about the angle in this bottom left corner, as that approaches 90 degrees, my adjacent side is getting so small. My adjacent side actually approaches 0. So let's actually write that down. As my theta approaches 90 degrees, my adjacent approaches 0. Because my adjacent's getting so small to compensate. And as this gets done, my opposite, it's approaching whatever number, but it's, as we get a bigger and bigger angle, it becomes the effect of dividing by 0. Now, this is not an O for opposite, this is a 0. Let's actually write that in explicitly. as the angle gets bigger, as the angle approaches 90, my adjacent approaches 0. So when we look at tan theta being the opposite over the adjacent, I get the opposite side over something really, really close to 0. So what happens then is, well, we can't divide by 0 in maths. So we say that the tan of 90 degrees is undefined. And just like that, we have used our two, we call these, some people call them magic triangles, these ones. These are the most significant triangles we deal with for the remainder of trigonometry in high school. So these are all the main ratios we come across, the ones we've written out here. And when we make this into a table, this is a nice little summary of all of them that we have here. And we also looked in this video at some of these extreme cases. What happens when theta is 0? What happens when theta is 90? And this will come in play quite a bit when we work on some of the later topics. But that brings us to the end of this video. We will look at some practice questions for exact values in the next video. So thank you so much for watching, and I'll see you there.